helpful. An ion exchange column may give you a 10-fold purification. An immunoaffinity column can give you a 5,000-fold purification in one step, because there's really only one protein that has the epitope that the antibody binds to. The problem is, in the past, is that the antibodies have bound the antigen so tightly that it was hard to elute, and people had to use pH 2 or pH 10 or use guanidine hydrochloride or something pretty harsh, and it wasn't very good if you wanted to do something with the sample afterwards other than say you purified it. So what we looked for, I spent a year on sabbatical in a biotech company in Seattle in 1983, 84, and what we looked for was that there's a company that specialized in making monoclonal antibodies. It was also started by a friend of mine, so it was easy for me to arrange this. And I was looking for antibodies that would bind tightly but release under mild conditions, not harsh conditions. And what I found is a category of antibodies which we call polyol responsive. It elutes with polyols like propylene glycol or ethylene glycol or butanediol. A couple of my graduate students made this slide. The general idea of immunoaffinity is you've got beads that have covalently attached antibodies. You put through a mixture of proteins. You get the one you want, and there may be some others there. You wash away the things that are not most tightly bound, and then you, in this case, elute with salt polyol, and you get very rapid and very effective purification. So I won't go into detail here, but we've tried many different coupling reagents to couple antibodies to columns, and to be honest, we still find that cyanogen bromide activated Cepharos is a very good way to do it. It has only one problem, and that is that the chemical bond between the antibody and the bead it leaches off slowly. But otherwise, you get 100% coupling, and we can get antibodies coupled on that are very efficient still at binding antigen. So, as I said before, often you have to go to harsh pHs or chaotropes. Sometimes cold distilled water or magnesium elute things off, or sometimes you can elute antibodies off or antigens off of antibody columns with a peptide epitope. Sometimes you can add a ligand. There are now examples of antibodies that bind in the absence of calcium, but calcium, when you add calcium, it changes the conformation of the antibody and it releases. Those are things that you just have to screen for, but that's not so hard to do. But what we found is that a combination of salt and polyol worked. Now, here's an example of what was being done in '83 in a relatively crude sample. Here was put on an antibody column, and this is what eluted off. So, I mean, this is powerful purification. What they had to elute off with 2 molar guanidine hydrochloride. About that same year, a very important paper came out that pointed out that you could screen for and find antibodies. In this case, the previous antibody, they had to go to almost pH 2 in order to elute off. This one you elute at pH 4, so you could find an antibody that eluted under milder conditions. Same way here, the old antibody eluted at pH 11, and this one eluted at pH 10. But pH 10 or pH 4 are still, in my opinion, harsh conditions, and I would prefer to have it be under more gentle conditions. Just some, before I get into this, some tips. first of all, actually, monoclonal antibody immunoaffinity columns are probably not very applicable to most people, unless you have the ability to make your own to grow monoclonals. They're very expensive. I can make monoclonals in my lab for $1 a milligram, but usually you would pay, if you buy them for Western blots, an antibody costs $350 for, the U.S. probably $1,500 here for 100 micrograms. So it's something that's pretty expensive, unless you're in the position of growing up hybridoma cells and producing antibodies. But it's extremely useful. You always want to wash your resins well before you start using if you've made an immunoaffinity resin, because to remove any leached off or released antibody. You want to avoid dithiazolidinol in your buffers if you can, because that will reduce antibodies and cause them to inactivate. You can actually bind right on the column. Just pour the sample onto the column. You don't have to mix with the beads ahead of time. You want to elute, but not super fast. You can reuse these columns. We've used them as much as 10 times, where we do a brief stripping of any cellular material that's clogging the column with potassium thiocyanide. But it has to be a brief, because the potassium thiocyanide is a strong aerotropic agent, and it can damage your antibody. You want to store it azide to prevent things from reacting, from bugs from growing in your resin. And what we found actually, and this is a really important tip, you don't want to spend your money and get the antibody, make your column, and then find out that after storing it for 2 months in the refrigerator that it's all the antibody is leached off. But we found that since the chemical reaction, it's slowed down by lower temperature. And by what I mentioned yesterday is that adding 50% glycerol is just magic when it comes to stabilizing things. So we can put in 50% glycerol and store at -20, or we could even store at -70. And it doesn't damage the immunoaffinity resin, and it slows down any chemical bond breakage that leads to leaching. And this is sort of surprising. Sometimes you are told you can't freeze chromatography resins like Cephirose, but you can if there's glycerol. So why do you want to use monoclonals instead of polyclonals? Well, first of all, you don't need very much antigen in order to immunize a mouse. 50 to 100 micrograms is enough. And it needn't be completely pure, because you're going to select for the hybridoma that is directed toward the antigen of interest. We often immunize with, let's say, RNA polymerase, which has 5 subunits, and we can get hybridomas out of that fusion to all 5 subunits separately. So, in fact, it's a way of making things cheaper. If you have 2 antigens you want to do, you can co-immunize with both of them at the same time, and it's the same amount of work, but you end up getting 2 collections of monoclonals, once against one antigen and one up against the other. Once you have a hybridoma, a cell line that is producing that one particular antibody, you can freeze it away, the cell line, and at any time in the future you can thaw it and grow it up. So you have an indefinite supply. On the other hand, with polyclonals, some of you probably had the experience of having a good one, and then when it runs out, you can never get one that's as good again, because it's a different rabbit. And so this is a reproducible, indefinite supply. Essentially all of the antibody in the sample is specific to your antigen, whereas in a polyclonal, there's a lot of other antibodies, unless you do antigen purification. The most important thing is that because it's one antibody with one binding characteristic, you you don't have a mixture. If I have, let's say, a mixture of antibodies in a polyclonal to different epitopes and with different binding constants and different dissociation properties, I can't do what I'm going to tell you I do. If I'm able to screen 10 monoclonals, I can find one that has good properties. Because each one is different, but it has a defined characteristic. So, for those of you who don't do this, this is almost exactly like just making a regular monoclonal. You inject a mouse. After boosting, you take the spleen out, you separate the cells, you fuse them with a myeloma cell line, which is a cancer cell line, so you have a hybrid cell which has the indefinite growth and culture of the cancer cell and the antibody production ability of the B cell. And then you basically look among hundreds of hybridomas for the ones that produce antibody against your antigen. You screen these by an ELISA type-based assay. And then we use once we have those, we actually screen them again and by another method I'll tell you about. Then we clone the hybridoma, so we have a single cell line producing a single antibody. We then optimize how to bind and elute, prepare the antibody, prepare the immunoaffinity column, and we use it to purify the antigen. So the ELISA elution assay is, as you probably know, this is a well in a microtiter dish. You coat the well with antigen, then you put in a sample that may have an antibody. If there's an antibody that binds to your antigen, it will stick to the antigen. Now normally you would just wash that, and then you put in a second antibody to the first antibody that has an enzyme on it, and then after washing that, you would add a substrate that produces a color. So this is the typical ELISA. What we do is do this with a regular wash, but we also then in parallel do a wash with high salt polyol. Something like 1 molar sodium chloride, 40% propylene glycol. And what happens there is that if the antibody binding to the one that's being made by your hybridoma is able to be released by the salt polyol, then it will come off, and so you'll have a lighter color, lighter signal. You will have removed some of the primary antibody, and so you're basically doing a little reverse immunoaffinity column right on the plate. And so we can screen hundreds of things this way, on one plate. Hundreds on one plate. So this is, and what we do is to say, if washing with salt polyol gives you a signal in the final when you read the plate of 50% or lower of the sample that was washed with just buffer with no salt polyol, then we call it polyol responsive. So here's an example. My wife and I did a mini sabbatical in Melbourne, Australia about 15 years ago, and they had a collection of rat monoclonal antibodies in the lab at the Walter and Eliza Hall Institute in Melbourne to various parts of the apoptotic machinery. And here's an example of an antibody. We coat the plate with an antigen, and here's a dilution series of an antibody, and then washed with buffer, and here's buffer plus salt polyol. You see they're about the same. Whereas this one, with regular salt buffer wash, you get a good signal, but when you do it with the salt polyol, you get a much lower signal. And that shown here, if you just plot the thing. So this is the concentration of the antibody added. You can see that as you dilute it down, the signal gets lower, but this difference between the tris-EDTA buffer and the tris-EDTA salt polyol buffer is essentially there's no difference. Whereas in this one, there is. And so we would say this antibody is a polyol responsive antibody. And when we did this early on, here was an example of some that were 2-RNA polymerase, and you see these things, that this is buffer plus salt polyol. Most of them, there's no difference, but this one, we had a big drop, and it's number 73, and we then called that NT73 after my senior scientist, Nancy Thompson, without whom none of this could have been done. And so anyway, NT73 is an antibody that we've studied a lot. And it's extremely useful to purify RNA polymerase, bacterial RNA polymerase, and it turns out it works on almost every bacterium because the antigen that it binds to is highly conserved among prokaryotes. And therefore we can actually purify RNA polymerase from just about any bacterium we want to. There's a way to improve that probability. You immunize your mouse with E. coli RNA polymerase. You boost it with E. coli RNA polymerase, and the very last step, you boost it with B. subtilis RNA polymerase. A B. subtilis is gram-positive, E. coli is gram-negative. They're quite different, yet they have high homology between their RNA polymerases, and we selectively boost the B cells that are stimulated by the B. subtilis, and that way we get a cross-reacting antibody to all bacterial polymerases, essentially all. So this was the most revealing thing. We did an ELISA elution assay. We washed with, this is now with our antigen on the plate with NT73 as the antibody. And we washed with TE, TRIS-EDTA, we see a good signal. If we wash with salt, we see a good signal. If we wash with ethylene glycol, we see a good signal. But if we use ethylene glycol and salt, we see a decrease. We use propylene glycol plus salt, butane-diol plus salt. So many of these, but not glycerol so much. So somehow the polyol and the salt together synergize. And to be honest, we don't really understand why this works, but here's my theory. In an antibody, you have CDRs, conformation determining regions, or complementarity determining regions. And they can bind to the antigen. I think what happens in these antibodies is that they have to stretch a little bit to bind. But when you add salt polyol, it tightens up the structure of the antibody and it distorts that binding site, and they get weaker. They don't get 0. They go from 10 to the minus 9th, 10 to the minus 10th to 10 to the minus 6th binding KD. So if something has a binding constant of 10 to the minus 9th or 10th, it's going to have, you can wash it for an hour. If something has that binding constant of 10 to the minus 6th, it comes off in a second or two. So that's when things elute. It doesn't mean they have 0 interaction. It just means they come off so fast. So anyway, this allowed us. We ended up choosing propylene glycol. Propylene glycol because it's less toxic. It's used in food actually. Whereas you don't want to put ethylene glycol or butane-diol in your food, and butane-diol is expensive. So anyway, propylene glycol is a very suitable thing for doing this, and almost all of our experiments then. So here's the other thing. So I can wash with the ELISA plate with many different concentrations of polyol or many different concentrations of salt, and I won't elute. But the mixture of salt polyol, this is higher. This is ammonium sulfate and propylene glycol, sodium chloride and propylene glycol. So we just choose a salt and a polyol that will give us good elution. Here's an example. Here's a crude extract of E. coli. Crude extract, just spin out the debris and put it on the column. This is the flow through. It's so overloaded that it's bad. You can't see much. Here's the wash with half molar salt. Remember, half molar salt doesn't wash off the polymerase. In fact, a little bit comes off. But when we put the salt polyol on, wham, This is the beta prime beta, sigma, alpha, and omega subunits of RNA polymerase. Turns out this protein is called Rep A. It's another RNA polymerase binding protein. So we were able to purify polymerase and bound factors. I mean, this whole thing took 15 minutes. So it's really powerful. Now the most notable, and the generality here is that we can almost always, 5 to 15% of the time, I would say, we can find a polyol responsive antibody in a collection of monoclonals. So if you have a collection of monoclonals, you can actually do this, and you can find out whether any of those could be suitable for immunoaffinity column. It's easy to optimize the eluting conditions. You just do an ELISA plate with varying conditions and see what happens. They're high affinity under binding conditions, but they're low affinity in the presence of salt polyol. These are very mild conditions. Ammonium sulfate and propylene glycol are both protein stabilizers, as opposed to harsh, extreme pHs or chaotropic salts. You get a high recovery of active N protein. It's no more complicated than a normal monoclonal antibody isolation. And we've done this on literally hundreds of different transcription-related proteins. So it's very general. The most notable one is an antibody that Nancy made to the C-terminal domain of the RNA polymerase II. Now this C-terminal domain is again conserved among all eukaryotes, and so it's called the antibody is called AWG16, and we made and provided probably 100 milliliters of immunoaffinity resin to Roger Kornberg at Stanford, and he was trying to purify yeast RNA polymerase II in order to get crystals, and he had been unable to get crystals because it took too long to purify. The protein is a 12 subunit complex. It was heterogeneous, it didn't crystallize. Using our method, we were able to purify it in 3 times faster with a 2 times higher yield and 3 times higher specific activity, and they got crystals right away. And he went on to get the crystal structure of yeast Paul II and won a Nobel Prize. We're on the paper, Nancy and me. So I mean, this is an example of how powerful this was and why it was useful. It was able to purify rapidly a labile complex. Okay, sometimes you don't want to go through all this. You want to just take the epitope that is recognized by a polyol responsive antibody and stick it on yours. And we've made 4 different epitope tags that bind to 4 different well-behaving polyol responsive antibodies. So I've already said this, that this is really a general procedure. And if you wanted to, say, pull out a polymerase, a complex A, and there were a protein A that had a complex with AB and then another complex AC, you could pull out the mixture of AB plus AC, and then you could do one more column step afterwards to separate these 2 different complexes. You couldn't do that if you had treated this with 2 molar guanidine hydrochloride or pH 10. You would have knocked apart, you would have inactivated your complex. So the gentle immunoaffinity is the key here. Okay, this is just an example of locating out of a 1,400 amino acid long beta prime sub RNA polymerase. We located an epitope by just cloning various pieces and seeing which ones react with the antibody. And so we know that this will react, and we published this. And we found that if you put this tag on GFP, that it behaved pretty much the same way that RNA polymerase would in terms of elution properties. So the polyol responsiveness is a property of the antibody, not of the antigen. Okay, and here's an example of using that. Here's a E. coli where we've overproduced a little bit of GFP. This is the flow through from the immunoaffinity column. This is what eluted off. Now notice it also has beta-beta prime. That's because this is an antibody to RNA polymerase. So it also purified the RNA polymerase that was present in the extract. But this was an extremely quick way to purify this protein. And here's an example. This is fun. I used this to teach about immunoaffinity in my course at Cold Spring Harbor for 22 years. And Nancy came up with the idea of using GFP as a visual aid. And so here you have a 2 mil column, you put on your sample, you bind your fluorescent, your epitope tag GFP, you then wash it, and then you elute off. And that's the purification. It's very low tech, but it works beautifully. This column, 2 mils, has about 5 milligrams of monoclonal antibody on it. But I can use it to purify almost 5 milligrams of antigen. So, okay, this is where we were. We had monoclonal antibodies whose binding was modulatable. We could change the binding constant by just changing the salt and polyol. And along came my colleague David Beebe from the biomedical engineering department. And he said, Dick, he had taken my course as a student at Cold Spring Harbor, and he knew I loved proteins. And so he said, we have this new technology, but we haven't shown that it works well with purifying proteins. Would you work with us? And we said, sure. So we, in fact, used the system of the antibody to the epitope tag and using epitope tag GFP as our sort of a model system. And that was 9 years ago when he came, and they were trying to get some preliminary data for a Gates Foundation grant. And in fact, with our data, we were able to get a grant, a 3-year grant, and a lot of the work was done on this using this Gates grant. The idea was to develop a rapid diagnostic that was very cheap and could be used in Africa or somewhere where there weren't sophisticated diagnostic laboratories. So we used, in this case, another antibody, 8RB13, and an epitope tag GFP. Okay, so I'll try to be brief on this, but there is something they called ESP, or exclusion-based sample preparation. And there were 2 forms. One was called IFAST, where you had silicone gels with wells on a glass slide. And another one is called slide. This one, you actually drag you put magnetic beads in to bind here. You drag them across a well of oil, of olive oil. We used olive oil at first, but no balsamic vinegar. But we would go through oil and into a buffer, into oil, into a buffer, into an oil, into a final sample. That's if you wanted to do 3 washes, which we really didn't need. Okay, so here it is. You start off with a crude lysate with a magnetic bead that has protein G, which binds antibodies. You load it with the antibody you're wanting to use, and then you mix it together. The antibody binds to the ligand, the antigen. Then at some point you put oil in here, and because of this being very microfluidic, very small, the oil and the water don't mix. And so you then take a magnet and you just pull the beads through the oil into this. And it's remarkable. It takes 1 second, and you've purified the protein of interest that your antibody is binding away from all the other proteins. So I think, so the epitope tag GFP is the analyte. The affinity reagent is monoclonal antibody. We use these paramagnetic or magnetic beads. that are coupled with protein G. The immiscible phase is either oil or air, as I'll show you. And now let's see if this works. So here's a plate, and it has 5 identical experiments. So we're putting in that's the output buffer. These are 8 microliter wells. And then this is the onput well that has the magnetic beads and the immunoaffinity reagent in it. And then here is I think this is some kind of a silicone oil or some kind of a mineral oil that we put on in the middle. So now we can do 5 parallel experiments here. And we can do hundreds. I mean, you can fabricate these things any way you want. Then we take this slide, take a little pile of strong magnets, and we move it across, and you see the beads they go through the oil and into the other side. And that's it. We just purified protein from 5 samples in 1 second, or 2 seconds maybe. So this was pretty exciting, I have to say, because this could be anything. It could be you're looking for a tuberculosis antigen in a sample. You're looking for HIV. You can use poly-U. You can use a bead that has a sequence that will bind HIV RNA, and you can do viral loads. That's what they wanted to do in Africa, was do rapid test for HIV. And then all you do is a qPCR or something like that on the output. We've gotten it away from all the other junk in the starting sample. So this was pretty neat, I have to say. And here's just another example of this. Here's GFP in the initial well. We had RFP that didn't have an epitope tag as sort of the surrogate contaminant. We then moved it across, and now the GFP was on the other side and the RFP stayed behind. And here's the crude sample, and here's what we purified out. Now, people have used magnetic beads before. You do the same thing. You put your affinity bead in with your crude sample. You then let it incubate, and then you pull it over with the magnet. You remove the unbound stuff. You put in some buffer. You mix it. You wait for 3 minutes. You then pull the magnet over. You do like 3 washes. So the whole thing takes like 10 minutes. And we found that, and so here's an example of comparing this to conventional wash versus our IFAST. And the lift behind GFP was about the same, the captured GFP was about the same, the carried over RFP was about the same. But ours took seconds and theirs took 10 minutes. The conventional way took 10 minutes. So we were pretty pleased with this result. And we then just put some fluorescein dye in the starting well, and we just said here's how much was there, 100% in the starting well. Here's after 1 conventional wash, 2 conventional wash, 3 conventional wash, 4 conventional washes. So you see it takes several washes in order to get rid of this dye that shouldn't be bound. With our IFAST, 1 wash was already as good as 2 washes, and 2 washes was better than 4 washes with the conventional method. So not only are we able to capture stuff, we're able to do it fast, we don't have to do as many washes. So I said, this is pretty interesting. What are the implications of this? And I said, wow, you could isolate weak complexes this way. Things that would fall off during a 10-minute wash that wouldn't fall off in a few second wash. And so we did the experiment of this. My thumbs are too big. In the blue is a conventional wash, and in the red is our IFAST. And if you notice, this is a polyol-responsive antibody at very low salt. The binding constant is it's a tight binder, whereas at higher salt, it's a weak binder. So at very high salt, both the conventional and our method don't capture the fluorescent GFP. But at a higher binding, but still not super tight, the conventional method already loses stuff, and it loses at that. So if you're here, where you can barely see the bound material with a 10-minute conventional wash, we get a strong signal. This is basically IP, an immunoprecipitation, but it's being done in 5 seconds instead of 10 minutes. And so things that fall off, weak interactions, will be captured with our method and not with the conventional wash. So it turned out, to make a long story short, and echoing what Guy said yesterday, is that intellectual property makes a difference. And we were about ready to start a company called Oleon, which I think is the Greek word for oil, to use this passage through oil as a way of purifying. And a patent came out that should never have been issued, but it basically blocked any commercialization. So it was very frustrating because I used to give this talk and everybody'd say, I want one of these. And we said, well, we can't make a commercial product. So Dave Beebe's lab is incredibly creative. And they said, oh, we don't need oil. So they came up with a new thing called slide. And if anything, it works better than oil. So in this case, you have a slide or a dish, and you have a droplet of your onput with your beads and your crude sample. And you slide over the head with a hydrophobic surface. And there's a magnet inside here. And when you slide it over, the beads go up and stick to the little head, and then you slide it across. And then in this one, there's a magnet below with the opposite polarity, and it pushes this magnet up, and now the beads fall down into this little droplet. And you can then take this magnet and move it over one, and then this magnet will fall down, the beads will go back up, and you can move it over to the next one. So it's, again, a very rapid way of transferring the beads from this to this, but instead of using oil, it's using air as the, and it again works remarkably well. Now, you have lots of possibilities. You can move it from here to here. That's sort of the basic thing. You can move it from here to here and get a 40-fold concentration of your analyte. You can move it from here through a wash, drop it into a wash, and pick it back up and deposit it here. You can pick it up here, drop it here, pick it up, drop it here, pick it up, and go there. And I'll tell you later, you could, if you're looking for weak interactors, you could wash it, and then you could go over here and you could let the beads sit there for a minute and let any weak things dissociate, and then move the beads into antibody and protein G and everything that's bound tightly to the next one. So this is an example. I don't think this movie's going to work, but of a prototype where we had 4 samples with beads that we're going to move here, and then another 4 samples that we're going to move here. Again, hydrophilic spot where the droplet is, a hydrophobic all around, so you get a nice droplet. And you just move it, and it moves this one from here to here, and then you move it over, and then you move this one from here to here. So let me just see if it works, but I'm afraid this might not. Well, imagine this. You just move the slide and it goes click, and then you move it over and click. And the click is the magnet going up and the beads dropping down, and then you move it to the next one, you pick up the beads, and you move them over, click, it goes down, it goes click, click, that's it. So this is very rapid. Dave Beebe started a company, and I should disclose that I have a small equity in this company, but not much. But to commercialize this, and it's called SALUS, S-A-L-U-S. But we collaborated with Gilson, famous maker of Pipette Man, and they made Pipette Man, I guess, and they made this thing with a lot of input from us on. It's called Extract Man. And it's a gadget that commercializes what I just showed you. And you can buy plates, and you can buy the little heads that fit on top of the sliding head. And in fact, while the plates are a little expensive, you can reuse them many times. So anyway, this is, and there, I think there's a link to this. If you go to Google and just look Gilson Extract Man. Okay, now I want to finish up by talking about weak interactions. So, and I've already mentioned this a little bit. If X binds to Y to form a complex, if the binding, the equilibrium dissociation constant is nanomolar, then with some assumptions about on rates, you can estimate that it's about a 30-minute half-life. It will fall apart with a half-life of 30 minutes. If you drop the binding constant 10 to the minus 6th, or micromolar, this is a weak interaction, and the half-life is about 2 seconds. So it turns out that it's known that there are weak protein-protein interactions. In fact, they're very important. All the proteins that are involved in post-translational modification, so writers, erasers, and readers all bind weakly. So in many cases, they've never been seen. Because if you isolate a complex and you wash it, it's on a column and you wash it for 10 minutes, you've washed off all the weak interactors. So we said, gee, maybe we can use this to isolate those important but basically invisible components of these complexes. And I think when I started graduate school, the idea of a protein complex was pretty big. People didn't realize, but now as we know, transcription, translation, replication, apoptosis, proteasomes, signal transduction, they're all carried out by quite complex protein, multi-protein complexes. But the things that regulate those are often hit and run. A protein comes in, it binds, it puts on a phosphate, and it leaves. It doesn't have to stay for a long time. Yet that protein has been an important regulatory protein, and yet, in many cases, people don't know what they are. So we decided to write a grant called Seeing the Unseen. And it took us 5 attempts, but we finally got it. And we've been working lately on it. So again, the problem is that if you have an antibody binding the yellow protein, and there's a weakly bound protein, if you keep washing it in the conventional method, by the time you get to the end, there's very little of the red protein left. It's all come off, whereas if you can isolate this very rapidly, you can capture that weakly bound protein. So I've already talked about this. I went to a meeting in Boston a couple of years ago on using protein-protein interactions as a site for drug discovery. And I think it's important to note that people used to say you couldn't find a drug that would inhibit a protein-protein interaction because it was too strong. But you can. And people are doing it all the time. But it's easier if it's a weaker interaction. So if it's an important regulatory thing and it's weak, it's an easier target for drug discovery because you don't have to use this high concentration of the drug, and therefore there are fewer side effects. So we think this has potential to come up with some really interesting new drug discovery targets. Okay, so the technologies allowed extremely rapid separation, got excellent yield and selectivity, extraordinary speed, low dosage usage of affinity reagents, a starting sample, flexibility. We can do just about anything with this. We took advantage of our epitope tagged GFP and our polyol responsive antibody to modulate binding efficiency. We can easily isolate enough to see in a silver stained gel or a Western blot or by mass spec. So this isn't a preparative in the sense that I can make 5 milligrams of protein this way, but if I can get 5 micrograms or even nanograms, it's going to be enough to do a lot. What we're now doing is to use this to isolate weakly bound proteins of complexes and then analyze them by mass spec. I'm telling Pia, if you do this trick of washing and then putting it in a dissociation well, you allow the weak binding things to come off in, say, a minute, and then you take the beads that contain protein G and the antibody and the tightly bound stuff out of the way, and now you can do your mass spec test on this enriched sample of bound but weakly bound, and that should increase our ability to see things. So this, I just want to say in closing, this is a very flexible technique. You don't have to use antibodies. That's your affinity on a bead. You can use poly-U and you can isolate messenger RNAs. You can use antibodies to surface antigens, and you can use this as a cell sorter. You can separate, they're using this to separate circulating tumor cells from blood. Very rare cells, but they can easily be purified this way. You can use this to isolate, put on the DNA sequence and use it to capture a specific DNA binding protein. You can, anything that involves an affinity, you can do this way by just varying what's on the bead. You can put streptavidin bead, and you can use it to pull out biotin-elected proteins. You can use a nickel chelate bead, and you can use it to pull out this text protein. But I think the biggest use will be for those people who are trying to isolate something that it's been very hard to isolate because it dissociates so rapidly. So again, this was a collaboration between Salas and Gilson, and the extract man is the product, and it's available. They also, by the way, have a robotic. They have a high throughput version of this, but most laboratories are going to want to just have the little gadget do this. And here's some references. Okay.